let's give you a list of what we're up to today. Well, we are going to essentially look at section 7.7. We should hopefully know how to do estimates of areas under curves using things like left 5, right 5, and midpoint 5, right? Actually, see, once you've done one of them, haven't you done every single one of them? I mean, all they do is they change the start and finish number and they change the function, but you don't change the process. So we're going to move on to 7.7, and 7.7 adds 2 more techniques for estimating the area under a curve. And these 2 techniques are going to be called the trapezoid rule, and lastly, the Simpsons rule. And because it takes so long and there's so much work involved in them, I'm actually only going to give you one example of the process. But if you use this as a template, you pretty much know how to do every single version using these 2 rules. But we have a fair amount of setting up to do. So the question I'm going to use, I think there's 6 of them, yes. There's only 6 questions in 7.7, is example, question 2. So find the area of this curve from x equals 7 to x equals 10 and using 6 strips, and round off your answer to 6 decimal places. And we're going to change that. We're going to change that quite a bit. Firstly, that's actually not the way the question is going to be written. You're going to see it like that. Now, when you see this funny little, looks like a musical symbol, it's actually the integral sign. And integral is one way of looking at an integral is the area under a curve. So rather than have to use the words area under a curve, we do this. And so we would write this down as the integral from x equals 2 to x equals 5 of this function, and n equals 6, meaning 6 strips. And I'm going to change the question to 2 decimal places. And the reason why I want to change it to 2 decimal places is that you would be bored stupid if you had to do it to 6. Can you imagine doing calculations to 6 decimal places involves you writing down an awful lot of digits an awful lot of times? Would you agree with me that if you can do it with 2 decimal places, can't you do the process to 20 decimal places? The only difference is going to be, you know, how bored you get, how many decimals you have to type in. So I've adjusted the answer scheme in WebAssign to account for that, so it should work. So as long as you're doing the process right, don't worry about the question saying 4 decimal places, 8 decimal places, or 6. Pretend all of them say 2 decimal places, right? And just do what you would do, but with that accuracy. So what we have to do then is find the area under this curve from 2 to 5 using 6 strips. And we're going to use 2 new techniques that you don't know quite yet what they are, but we are getting there. And so the first thing we're going to have to do is set up our table. You know, the table where all the numbers are, right? Now I'm doing that thing they do in the cookery program. Actually, I'm going to change this. Can I change this to 7 to 10? There we go. Because that's what it says up there. Right. That's what the table looks like if you do it to 6 decimal places. Don't write this down because we're not using it. Can you understand why I don't want you to do it to 6 decimal places? Just for practical reasons. But we are going to do it to 2 decimal places, which is that table. So let me show you where I get these numbers to 2 decimal places for this function. So I'm going to zoom over. Hopefully this will work and show you how you get it on your calculator. Right, are you all looking at a TI-84? Right, okay. So I'll put the thing on. Let's just clear that out of the way. Make sure that your mode is in radians, as it should be for calculus. Type y equals and type in the sine and square of x. That would be fine, okay. Then what do? You then go to second table setup. And this one starts at 7. I've kind of missed out a bit. You start at 7 and you finish at 10, and there's 6 strips. Can you agree that 0.5 would be the delta part, right? From 7 to 10, cut into 6 strips, 0.5, 0.5, all the way up. So that's where that 0.5 came from. And you always leave these as auto. And then you go second table. Come on, there we go. And these are the numbers. If you truly wanted to do everything to 6 decimal places, do you notice that that screen only shows you 5? And you might think that's the end of the line. If you use your right-hand cursor, can you see the answer to as many decimal places as any human being would ever want? But now back to what the way we're doing it. That guy is just going to be called 0.48. And that guy is going to be called 0.39. And lastly, have you noticed that this last guy is a negative number, negative 0.02? And it's okay to have negative numbers when you do areas under curves. So I'm now going to return with that table that we had. And hopefully you'll say, okay, I know where you're getting the numbers from. Are we comfortable about where these numbers here came from? Right. They're straight 2 decimal place rounding off from that calculator that we just looked at. So I have just completed step 1, setting up the table of values, setting up these guys. Now, don't worry about the green and the red, they're coming later. That's this bit there. Step 2, we don't need to do this normally, but we do when you do the trapezoid in the Simpsons rule. Do you see these X values at the side? We'll label them. This guy is called X0, X1, 2, 3, 4, 5, and the last guy is called X6. And over here, that's where that 0.5 that I get. Remember the start take away the finish divided by the number of strips? That's why each strip is 0.5 wide. So far, so good. And that is step 2. And now we're going to calculate, using this table, the trapezoid and Simpsons rule. So let's get all these bits of paper out of the way. And we are going to use these data points, right, to get the trapezoid rule. But before we do that, let's actually kind of step back a little bit and tell you what the trapezoid rule is doing. So imagine you've got your typical function, just any old function, right? It starts at A, right? It finishes over here at B. And let's just say for argument's sake that it was 4 strips. We could use the left end point. That would be called L4, right? So if I took 1 strip and I used that side, the left side. If I took 1 strip, we get the right. If I picked the guy in the middle, wouldn't that get me a rectangle? And that would be called M4. But aren't all of them just rectangles? Right? So left 4, right 4, and M4 are rectangles. We just use different places on the strip to tell you how tall we want them. They're all delta X wide, but the height is different. So what did they do in what's called the trapezoid rule? Well, rectangles are okay, but do you know if you take this point to that point and you join it, you make a funny little shape that's basically a rectangle with a little sloping roof to it. And that shape is called a trapezoid. And that's why this technique is called the trapezium rule. Because it's full of lots of little trapezoids. It's full of trapeziums. Now, would you agree that this shape is a better fit than a rectangle is? So can you see that would probably give you a more accurate answer? So what I'm going to tell you now is what the formula should be. The trapezoid is a formula. I'm just going to, like magic, I'm just going to tell you the formula and you're going to say, okay, that's what it is. That's what it is. So the area, right, under the curve from 7 to 10 of the sine x fella, that's kind of the math notation for the area under a curve. It's equal to, well, approximately equal to delta x divided by 2 times the value of the function x naught, which is this guy, plus 2 times this fella, plus 2 times the next one. Guess I should have planned ahead here. Don't worry about this, I'm just rewriting it again, give myself more room, because I didn't plan ahead. Right. So it's the value of the function x naught, twice the value of the function x1, and the x2 and all the other ones as well. And the x4, twice the x4, twice the value of the function x5, and only 1 times the value of the function x6. So the way I'll think of this is it's a pattern. It's 1, everybody's 2, and a 1. And that's the formula, right? Where you just accept it is what it is, right? So delta x divided by 2 with all this stuff. So in my question, delta x is 0.5, so we divide it by 2. And then we do 1 of this guy plus 2 of this guy plus 2 of this one plus 2 of this one plus 2 of this one plus 2 of this one, and add that guy. And I know he's negative, but he still gets added, so it's negative 0.02. Just about made it. Are you comfortable that it's just, you tell me what to do and I'll follow your instructions? And my instructions are that you use all the numbers, not just the first 6 or the last 6. You use all 7 numbers, but you use them in a very special way. You use the 1 of the value of the function at the start, 2 times everybody in the middle, but only 1 value at the end, right? So that's what the 1, 2, 2, 2, 2, 2, 1 means. And then once you've added that up, you multiply it by delta x divided by 2. So on our calculator, 0.5 divided by 2 times, put a bracket around everybody, 0.48 and a 0.78 and a 0.62 and a 0.44 and a 0.28 and a 0.12, and then subtract 0.02, and the answer we get is 0.675, and that is called trapezoid 6. Would you agree it involves more work than doing a left 6 or a right 6, or for that matter, a middle 6? So the benefit is that it's accurate, more accurate, not perfect, but more accurate, right? At least in the left and the right 6s. So far, so good? Right. Yes?
I have a question.
Mm-hmm.
Why do we subtract 0.02 at the very end?
Technically, I'm adding negative 0.02.
Oh, okay.
It's because it's a negative number, I just got lazy and didn't say plus minus. I just said subtract it.
Oh, okay.
Now, that guy is called trapezium 6, right? And if you imagine how it works is that each strip is turned into one of these funny little trapezium. Can you see in lots of situations, won't that probably be a very good fit? So that's the benefit. You get a more accurate answer. The drawback is you have to do more stuff, to get that more accurate answer, right? So you kind of got to balance the two. Now, a couple of side things before we look at Simpson's rule. I'm going to break a rule that you've probably heard in your math career. I want you to imagine that I want to find the area under the curve of this shape, some of which is below the x-axis. So it starts here, let's call that A, and it finishes here, that's B. I'm sure you've been told you cannot get negative areas, at least when you were very young, right? If you went and said, what's the area of that box? And you said -2, wouldn't your professor look at you and say, can you really get -2 for an area? You know where I'm going with this, right? You are allowed negative areas under curves. It doesn't mean that it's a physical area. You won't be able to get a box where the lid is -2 square feet. I agree with you. You're not physically going to get that. But this is not an area. This is an area under a curve, right? It's a kind of special version of it. So negatives are allowed. For instance, if we take a function that you're quite familiar with, if I wanted to find the area under the curve of sine x from 0 to 2 pi, do you know that the area would be 0? And that is a positive, and that would be a negative contribution. And because they're the same shape, they would cancel each other out. So you might think, whoa, you're telling me that the area under that curve is 0. But I'm thinking 0 means there's nothing there then, right? It's area 0, you're gone. You're like a dot in space. I don't mean that. The area under the curve equals 0. Analogy. Do you know, if you've done physics, there's a thing called displacement, and there's another thing called distance traveled, and they're not necessarily the same thing. If I start at my front door and I walk 20 feet towards the main road, and then I turn round and I walk 20 feet back, isn't my displacement 0? Because I ended up where I started. But haven't I walked 40 feet? Right. So there is a difference, right, between one kind of area and a different kind of area. So maybe you want to think of these as displacements rather than total distance walked. I don't know if that helps. If none of those things help, how about, trust me, I'm a mathematician, you can get negative areas under curves. Will that work for you? Okay. So let's go back to our puzzle. How do you do Simpson's rule? Same table, different formula. It's called S6, and it's delta x over 3. And now the pattern gets even messier than the one we just looked at. It's 1 of the first guy, 4 of the next guy, then it's 2 of the next guy. Then it's back to being 4. And you do this 2, 4, 2, 4, 4, 2, 4, 2, whatever you want to call it, pattern. So here's 2 of this guy, 4 of this guy. And then you finish with 1 of the last guy. So you can think of that as a 1, 4, 2 pattern. Are you okay with that pattern? Do you see how it works? Right? 1 of the first guy, 4, then 2, 4, then 2. So Sabrina, what you want to ask?
Oh, I answered it myself before I finished asking it.
I am so good. Did you all catch that? Sabrina asked a question. I picked it up telepathy. I shot the answer into her brain. She didn't even know it was me. And it made sense. And she decided that she knew what was going on. I'm that good. I am so impressive. I scare myself sometimes by how good I am. Thank you. You know, I used to be conceited, but now I'm perfect.
On this one, is the
Yes.
are the first and the last values always just like just one, you know?
Correct.
Okay,
Always
thank
one.
you.
There's a lot of symmetry. Do you see these little green numbers that I told you to ignore? Now they make sense to you. When I do a trapezium rule, I normally don't bother writing things because it's easy to remember. One at the beginning, a lot of twos, and one of them at the end. But when it's a Simpsons rule, it's kind of hard to keep track, isn't it? Which one you've got. So I tend to just write down one of these, four of them, two of them, four of them, two of them, four of them, two of them, whatever, until I finish. And I finish on a one, right? If you notice, there's a lot of symmetry. Ones, fours, twos, fours. That means actually that you can only do Simpson's rule with 6 or 8 or 10 strips. Simpson's rule doesn't work with 13 strips. The pattern doesn't fit, right? Just a little. Nobody's going to ask you to do it with 13 strips anyway, but I just thought I'd tell you you couldn't do it anyway if they did try and ask. So in this guy here, delta x is still 0.5. Now it's being divided by 3. And it's one of these guys. 4 of these guys. I'm not going to risk that one. And the answer is 1.56. 2 of these guys. 4 of these guys. 2 of these guys. 4 of these guys. That's a decimal point. And 1 of those guys. So 0.5 divided by 3 times a bracket 0.48, 1.56, 0.62, 0.88, 0.28, 0.24. Technically, you're adding this last guy, so subtract 0.02. Oh, yeah. Okay, what did I forget? Looks good. What did I forget? There, I did. Did you notice that the thing I had was the negative sign, not the subtraction sign? That's what I did wrong. Okay, there's your answer. And the answer is 0.67 and lots of 3s. Are we comfortable with that, the process? Okay, I'm not going to do another one because it's already taking me about 20 minutes just to do this first one. Can you see if I did another one, this period would be over. So I'm relying on you to use this guy as your template for all the other ones, right? Essentially, just remember what you do with the value of the function, right? 1, 4, 2, 4, 2 forever, right? Any questions about the Simpsons rule before I kind of move on? Okay.
So what's the main difference between the Simpsons rule and the trapezium? Like the second formula, is it more accurate?
Yes, it is.
Okay.
Let me show you what Simpson's rule does. So can you imagine that was A and this is B and 1, 2. Okay, there's 3 strips this time. Well, let's be honest, you have to do 4. If we went and did all the combinations we've got, if I went that way, wouldn't that get me an L4? If I went this way, wouldn't this be a right 4? If I joined this guy to this guy, wouldn't this be a trapezium 4, right? So you might think, what on earth is left? What does Simpson's rule do geometrically? Well, you take a strip, and this is something you probably would never have guessed. You take that point and you join them with a little quadratic curve. So Simpson's rule has a strip with a little curve at the top, and it's a quadratic curve, right? And would you agree that curves probably fit functions closer than lines do? And that's why it's the most accurate. So in the big scheme of things, right, in the big picture thing, because you're always going to get exceptions. Can you imagine that if you only did 4 strips, that just by sheer luck, no other reason, L4 was very, very accurate. It just happened to be the way the curve worked, and the pluses killed off the minuses and everything came out really good. But that's just randomness, right? In the big picture, if you do a reasonable number of strips, and well, let's just call it LN and RN, right? Where N could be 20 strips, say, right? Those are the least accurate methods. If you use an L10 and an R10, you'll get an answer, but don't expect great accuracy. The next one is actually the trapezium. You might have thought it was going to be the midpoint, but the trapezium rule is more accurate than left or right for the same number of strips. Then the midpoint. But these two guys are very close to each other. The midpoint tends to win, but not by like 10 goals to nothing, right? It's like it wins by a goal, right? Just a little bit better, but typically a little bit better, right? In general. And then right at the end, I'm putting 4 in there, back to my letters, N. Simpson's rule, as long as you do a fair number of strips, don't try and do 4 strips with Simpson's rule. I mean, really do 8, 10, 12 strips, right? Give it a chance to get the ball rolling. By the time you get up to that kind of number, for the same number of strips, Simpson's rule will give you a more accurate answer than any of the others. Midpoint would be the next, trapezium would be next, and last, right at the end, is left or right. Sometimes the left's better, sometimes the left's not so good. So that seemed reasonable. Maybe these two are not so obvious, but does the rest seem reasonable that for the same number of strips, which technique would probably get you a more accurate answer? Now, a little side issue. Some people use this. You know that if you want to find T6, there is another way to do trapezium T6. I could even prove that to you. I don't have time. But see if you write down the formula for L6 and you add it to the formula for R6, and then you divide the answer by 2, do you know you'll get the trapezium rule for T6? Now, doesn't that one use a number that the other one doesn't? And doesn't that uses the first number, and that one uses the last number, and don't all the other guys in the middle get doubled up? And can you see how that 2 comes out with the delta x, and that's where the delta x over 2 comes from? So the trapezium rule. So here's a little trick for you. If you ever get a question that asks you to get L6 and R6 and then T6, wouldn't you probably do this for T6 because it's just easier? You've already got most of the numbers anyway. So far, so good? Right. What I'd like to do is talk a little bit then about calculating errors. And so, let's go back to my original question. My original question was the area under the curve from 7 to 10 of the sine of the square root of x dx, right? And I would like to know what the error is. And the only 2 guys that we calculated were these 2. So I believe I've got 0.6733 and 0.675, right? Now somebody says, okay, what's the error? Well, don't you need to know the true value? And then won't the error, won't it be the true value, take away what we think it is? Does that seem reasonable? The difference between what the right answer is and what the estimate says. And the same thing's true for this one. It's going to be the true value, take away our estimate. So you might think, how do we get the exact value of that? Well, guess what? We can use our TI-84. So I'm going to go y equals and type in, already done it, right? Saying, I'm going to go to the window. I'm going to say from 7 to 10. Okay. From 7 to 10. I'm going to go zoom 0, which basically just sketches the thing. Pretty boring curve. It's almost vertical. It's almost a straight line, isn't it, really? Pretty boring. And now, I don't know if you've ever used this button before, but second calc. Do you see guy number 7? Do you see that funny little musical symbol, the integral symbol? Choose option 7. The lower bound will be the start number, which is 7. Press enter. The upper bound would be the finish number, in this case 10. Press enter. Then a little animation goes on. And the answer is 0.676. Okay, roughly. So what's our error going to look like? Well, if you take 0.676 and you take away 0.675, the answer for this error, that's pretty impressive, isn't it? Right? Trapezium 6 has gave us an answer that's only what, third decimal places out. Pretty good. Now, Simpson's rule. Let's round this off a little bit. 0.673 gives me 0.003. And I know you're going to say, wait a minute, you said Simpson's rule is more accurate than the trapezium rule. And how come it's not in this particular case? Well, the reason why it's not is that I did say, didn't I, in the big picture of things, I'm not going to do it, but can you trust me? If I did 60 strips on Simpson and 60 strips in trapezium, the Simpson's rule would murder the trapezium rule, right? If the trapezium rule is great to 8 decimal places, Simpson's rule will be great to 20 decimal places, right? It will start pulling away, right? So we're just at the beginning of the race where, you know, sometimes a guy's in front, but in the long run, Simpson's rule passes him by miles. So you're going to trust me on that part, that it will, in the long term, be the most accurate answer. Any questions about that? Are we good? Are we good? Oh, fingers up. Right. Let me use our time then to show you what those questions look like in your homework and how we're going to adapt them. Because you may have missed the beginning of today. And if you did, you would really be sorry if you didn't pick this up. Question 1. Here is the function. So it's going to be the area between 0 and 1. There's your function. Use a trapezoid rule and a midpoint rule with 4 strips. So can you imagine doing the work and putting your answers in there? And then it talks about unders and overestimates. So I think you might want to kind of sketch that and see, and the small number goes there and the big number goes there. So whichever one of these is the smaller is the underestimate, and for which one of these is the bigger is going to be the overestimate. And there's some stuff we can worry about. Trapezoid rule, there's the guy I've got. Do you see there's a trapezoid rule and there's a Simpson rule? And to do the midpoint, what you just do yesterday's stuff, won't the table be a little bit different for the midpoint? On front of me here, in this little piece of paper, the first guy was 7 and the next guy was 7.5. So if I'm doing the midpoint rule, won't my first number be 7.25? And then I build it from there. And there's all the working for it. You don't get the working, by the way. My version does that. Here's an ugly, ugly looking function. 6 strips, trapezium, midpoint, Simpson's rule. Wouldn't that be pretty much identical to the one I've just did? Right? Here's guy, 4. Oh, Simpson's rule with 4. I've got to show you that. Glad I did this. When you have only 4 strips, Simpson's rule looks wrong, or it looks kind of weird. Okay. If you're doing Simpson's rule 4, it's delta x over 3. You get 1 of the first guy. You get 4 of the next guy, right? That looks good. Shouldn't you get 2 of the next guy, 4 of the next guy, 2 of the next guy, 4 of the next guy, right? But unfortunately, since you've only got 4 strips, two of that guy, 4 of that guy, and 1 of that guy. I take it back, it makes it. Actually, I thought it was going to lose its 2 turn, but it didn't. It made it 1, 4, 2, 4, 1. I didn't need to do that. It worked out fine. There was a 2 turn. Right, let's return back, if I can make this work. See what's going on. Ah, wrong one. Here we go. There's question 4. Just talked about that one. Now, in this picture here, you're going to try and find the area of, looks like a bean to me. So, A is the start number and B is the finish number. These 6.2s and so on are part of a 3-meter interval. So from here, it's 0, and over here, it's 3. These 4.8s and 5s are just telling you how far it is from there to there. So A is 3. A is 0. My apologies. It's 3 meters from start to finish. So I want you to imagine that these little lines come down and along the bottom, there's like an x-axis, right? Think of it like that. Now, delta x then, if you take from 0, x is 0 to the end, x equals 3, and you split it into 8 pieces, won't delta x be 3/8, which is what? 0.375. Now, this guy is going to be 0. And then the next one, 0.375. And then the next one is another 0.375, which is what's that going to be? 0.75. Okay. Can you imagine me just continuing dum, 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 dum? And when I get to that last one, won't it be 3? Now, for each of these x0, x1, x2s, won't they be the x values on my table? So who would be, if they had some room over here, who would be the function value? Well, what is the, I don't know, height of this peanut shape when x is 3? Well, the answer would be at that side, at x equals 0. It'd be 0. Now, what about this position, which would correspond to that number? It would be 6.2. I'm just using this to write it. And then the next one would be 7.2. Do you see that you can actually, eventually, you can suck out a table from this? Isn't that a very unusual way of giving you information? But the x coordinates, these guys come from position 0, 3 8, 6 8, 9 8, 12 8, all the way to the end 3. And then the value of the function, these 3 numbers here, come from, well, it doesn't have anything, then it's 6.2, and it'll finish, would it also finish on a 0? So that one down here, was finished with a 0. Now, if you wanted to do Simpson's rule, wouldn't you do that number divided by 3 And then you'd say 1 of these, 4 of these, 2 of these, 4 of these, 2 of these, 4 of these, 2 of these, 4 of these, and 1 of him. And you'd get it. I'm not convinced I'm doing this very well, but do you get what I'm trying to say? Even though I'm pointing a lot and not really writing a lot. Okay, doing better than I thought. These are nice because if someone gives me a table, I really don't need to worry much about the rest, do I? All I need to know is who is delta x, right? And, you know, how many strips I've got. Imagine this was one big table. The reason they put it in 2 columns is just for size. What is delta x in this question? I guess I could call it delta t.
0.5.
Agreed. In fact, see if you don't know, wouldn't it be a good idea just to say 0.5? Because I don't think I've done many questions where it wasn't, but it is 0.5. Now, if you're doing Simpson's rule, won't it be delta x divided by 3? Right, Simpson's rule, delta x divided by 3. So 0.5 divided by 3. And then wouldn't you say 1 of these, 4 of them, 2 of them, 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 4 of them, and 1 of them. And you're done. Big horrible calculation. Make sure you hit all the right buttons and you're good to go. And that's what it looks like.